Hi everyone, my name is Steve Loughran. I am giving a talk called The Age of Rename is Over, mostly. As background, I work on the open source big data stack, Hadoop, Spark, HBase, all that kind of stuff. Anyone in the audience play in that land? Well, that's probably, okay. Any audience use, okay. Well, somewhere in there, in the stack traces is my name, all right? And I kind of have drifted into basically being the project manager for the open source connectors to the object stores. It wasn't intentional, but it happened. So I deal with a big chunk of the problem of reading data, writing data, reading it back again, trying to get that to work in this world. Question one, why on earth do we bother? Why do we persist things? And there's lots of uses. Sometimes it's temporary, some it's persistent. But when you think about it, saving state to some kind of persistent store is fundamental for applications around the planet. We take it for granted. We save things, we read them back. It's been going on for many, many years. Hands up who recognizes these other than the save icon on PowerPoint. All right, it's good, well done. In the elder days, we had DBase 2 for databases and Lotus 123 as our spreadsheet. That was where CSV files date from this era, of course, and DOS file APIs. A few hundred kilobytes per disk, I think. Things moved on. We ended up with hard disks. Now we have real file systems, ext3, ext4, not quite so real file systems, NTFS, and slightly better databases, copies of Excel. POSIX is the API in this world. Probably one of the great inventions of C and Unix is actually the API to dealing with data. Everything is a stream. Everything is a file you can open. Windows, it copies it, does it mediocre, but it's still roughly the same thing. Hands up who uses this as their storage. Hands up who's ever loaded a photograph to Facebook. Yeah, that's your storage. It's this Facebook Primeville facility. It has an exabyte plus of HDFS. Plus, they have arrays full of machines storing photographs that are powered off most of the time, so you actually want to retrieve a full resolution image. They basically power the machine on, grab that disk, power the thing off without even flushing it, just to keep your power budget down. So the storage density of this machine is if you basically built that data center, if you filled it entirely with those floppy disks, it would actually have less storage capacity than what they have up and running in there. All right, so that's the way the world is going. It's basically between Google, Facebook, Microsoft, and Amazon. There's a battle for whose data centers hold all your data. So how do we work with that data? We use a file system. That is the world we live in. Files, directories, POSIX. And, you know, it's come a long way, but we still try and preserve that metaphor even today. We have file system APIs. We might talk to a real file system here, like HDFS. But I also end up with the object stores as well. I deal with the S3A one. I co-wrote that. The Microsoft ones I don't deal with, but they get to file bugs against me. We have this relationship. So I get to answer support calls, even though they do the engineering. So everything says, OK, they're all just file systems. And we live in this world, all right? So Scala. Anyone programmed in Scala yet? OK, that's 4 people that recognize this code. I'm opening a file here. My path here says S3A, Steve, Frankfurt. I'm opening a file in Frankfurt. I basically create a directory there, create a path, temp directory under my work directory. Create a file there. I open an output file, say write hello to it, and close it. That's great. Some point in there, as soon as you open the file, it exists. You can stream data through. It'll get slightly bigger. Then you finish. That's nice and fast. The file exists at that point. And afterwards, I'm feeling excited. I take that file, I list everything in our directory, and I rename it to another directory. That seems a kind of futile thing to do. I say, why am I bothering doing that? But that is actually the fundamental aspect of the distributed commit protocol of Apache Spark. That's essentially it. You don't need to know all the details, but the point is that there is some Spark driver over here managing the entire job, the query. It farms the work out all to all individual tasks across your entire cluster, saying, read this bit here, do all your work, write it into a temp directory. When you're finished, send me a message saying, can I commit my output? maybe hang on a bit, okay, go and commit. You send a message back saying, oh, I've committed now. Then we go away, but otherwise it says, okay, if that thing timed out, then we've got a problem. It may have partitioned, it may have failed. Let's kick it off again, kick off another one. Even then, the tasks, they don't commit to the final destination until the entire job is ready to commit, because if the job fails, you don't want things full of cruft. And then finally go away and commit your work. So the goal is, no matter what fails, your destination data is in a mess. Now, if you think that's complicated, the MapReduce one is even bigger, because they have to deal with the fact that if you've got a query that could take something like 14 hours, it's how Verizon do their billing, something like that, is it could fail halfway through and you want to restart and recover, because otherwise people's bills will be late and we don't want that. So you have to do a restart, but then also it means your protocol for actually doing commit, you have to make sure that you haven't partitioned, so you don't want to commit the work while the second job is doing the same bit of work. So life gets really, really complicated. And we absolutely rely on rename to get this to work. Okay? The foundational semantics of pretty much everything, every database on the planet pretty much says, we avoid stamping on your old data by writing your new data next to it and then renaming it when we're happy. And it works because directories and renaming is atomic. I rename a file, data may be scattered all around my cluster, but if I do a rename, we just grab a lock on the directory tree and it moves. That is it. That is the essential bit. If you think about it, you realize you're doing it in all your code all the time. That's how you commit work, which is really good, except in the object store world, we don't get that luxury anymore. People think we're doing renames. We're trying to pretend that, yes, it's an object store. It looks just like a file system. You can read to it or write to it. But there are no directories. And there isn't even a rename either. You only have paths. So when we're trying to commit stuff, we have to list everything under the path. So list all the temp files under this task. We get that listing back. Then we have to do a copy. It takes about 6 to 10 megabytes a second. Finally, once it's there, said, OK, we're happy. We can do a delete. So we delete the old copy. There's some 3 flaws with that. One, we're doing a listing. S3 is eventually consistent. An immediately created file may not actually be visible. So somebody might write something, they commit it, and we miss that file out. We forget to copy it because we don't know it's there. Problem 2, it takes a long time. And problem 3 is, because we're doing this bit place by place, if something fails partway through, your system's in a mess and you don't know what state it is. So if you try starting another task to repeat it, you may be in a mess. It's not atomic, so these things will be corrupted. Now, in our documentation for Hadoop, the Hortonworks one, we basically say, do not use S3 as a destination, or we used to. And people would still do it, and they'd send support calls going, it's really slow. And I says, yeah, well, that's because you're using copy, but you see the bit where it says, do not use it as a destination. So one of my homework last year was to try and fix this. And the good news, with some help from people, we managed to do it. But it works. People are happy because they don't see the copy, but really they should be happy because they may not lose their data. What did we do? We just basically had to completely destroy the metaphor and start again. So you don't have directories anymore. You just have paths. And rather than rename things, we basically say we're going to write them straight into the destination. So we know that path. And we abuse a feature of Amazon that they added so you can add a massive, many gigabyte files and say, I'm going to do a multi-part upload. So I kick off an upload. I basically say, right, I'm going to write to this file, get my final path. And then I can push up blocks of it, a few megabytes at a time. And this data isn't visible until finally you complete the upload. So you do a put, a final post. So I can write straight into place, and it's not visible. Even if you're overwriting something else, it's just being, it just happens. Amazon still bill you for it before you think you're being clever and say, I can upload 4 terabytes, and they won't bill me. They will bill you from the moment it goes up, but at least you can put it there. And all goes up there, ready to go. So the tasks, they do their work there. They put all the data there, but we haven't actually set that final post to make it come into existence. Instead, all we have to do, we can get away with it, is getting the listing, the information needed to commit the job, which is basically the upload ID and the list of blocks you've uploaded. And we can postpone that right till the bottom part of the protocol to say job commit. And we just kick it off there and then. And it happens. We can do it. It's very fast. It basically takes is one post per file. We can parallelize it, irrespective of the amount of data. And, well, it does what it commits stuff. There's a bit more complexity to it, but I won't go into full details. But I'm about to give a shiny demo to show you this stuff really works, OK? I'll use this terminal here, I think. Oh, this is Spark for you. It's giving me noise. So I'm using Spark Shell here. I'm going to create some Landsat data, which I have locally. I have a file here. It's locally. It's a CSV file. If people have ever played with Spark, it's actually very good for working with data because you do not have to know SQL. I can say, here's a condition here. I want to filter it. You can do bits of SQL, but you can mix it with your code as well, like fractional sampling things. It's very cute. So now I'm going to write that data to data center in Ireland of Amazon's. I'm going to take that data. I'm going to partition it by year and month into files, and I'm going to commit it. Here we are. We're doing the work. We're uploading some stuff. You're really excited, you can tell, aren't you? This is just phenomenal. The point is that it worked, we did it, we committed. If something had gone wrong there, the demo would have been ruined, but the data would have been fine. Okay, and that's what really people want, and it's fast as well. It took six seconds to commit the work, 7 seconds, even over a long-haul connection. So we have done this. I'll point out, actually, this is in the open source Hadoop, but it's not actually in Amazon's EMR because they don't talk to us, so we're ignoring them. But this was actually done with Netflix. Actually, I developed with them, so they live in this world quite a lot too. And to show it's not completely fake, I'll actually print this little file out. We normally have a little 0-byte success marker at the end of a job, but since we can do atomic writes, we actually collect all the stats and push up saying how many bytes existed and how many bytes are read at the end. Oh, and we threw away a lot of data there, and we shouldn't have. And we actually count the amount of throttling that goes on too, which is kind of handy. People often say this job's slow, and you go through stats and you go, well, that's because you were being throttled. It's not our problem. So we have atomic commits. Everyone's happy. It's fast. This is good. So now we have to go back and work on the other problems, because if you look again, POSIX, it's kind of reaching its end of life, at least as far as these things go. You go through all our code, and we say, why is it really slow to kick off any kind of query? SQL query is because everything does recursive descents of directories. Basically goes, OK, let's have a look down the months and the years and get all these files. Tree walking is not the way to go in this world, not when you can do a single flat, deep listing of your entire pattern tree. So we're trying to think how to sneak that in without people noticing. Performance killer one. The other performance killer is if you look how everyone does their I/O, from the C era onwards, standard I/O libraries, you basically open a file, then we seek to an offset, and we read some bytes, then we seek to another offset, and we read some more bytes, and we go along like that. That kind of works when seeking is expensive, but not too expensive. But when we're doing object stores, we're actually, each of those seeks, you're not often breaking existing HTTP connection and kicking off a new one. We're doing HTTP GET requests with content lengths in. So it's incredibly expensive. There's a very high startup overhead. And it puts big gaps in the I/O. And what's really frustrating here is the applications, they know what bits they're going to read. If you're trying to read striped column data like ORC and Parquet formats, the big data formats, the application knows it's going to be reading this block and this block and this block to scan, saying, do I need to read these bits inside? Do I read it in a filter? So we know all this stuff. We can't communicate it to the file system because the APIs get in the way. So what we're now working on, and we've got some proposals up, is can we move to more of a scatter-gather I/O? So rather than actually seek and read, we just say, I'm going to give you a list of read operations. Here is the ranges, the offsets, the destination buffers. Then you get back an array of the asynchronous Java future callbacks. So you can start playing with asynchronous I/O on this, because things may come back in the order that's just up to the object store to work on. So we're doing this. It is a Apache Jira there if you want to come and play with. I'm trying to convince Microsoft to help me with this because it's hard work. So if anyone else can play, that would be nice too. Big thing we're trying to deal with is what about eventual consistency? We've done a lot of stuff to work around it and deal with it by trying to say we have to deal with using our DynamoDB to make Amazon S3 a bit more consistent. But it's kind of a real pain, and it's dangerous. Everything assumes that when you write a file, it's there immediately afterwards. When you look for it, when you overwrite it, it's immediately, you get the newest data, and that is not necessarily true. You can get the old data, or worse, as you seek around, you may go from new to old. So again, Netflix are doing something interesting called Iceberg, where they move beyond using the directory tree as just an informal way of representing data to some more basically storing the metadata in files of how your real data is stored, and generating a file with a new name every time. So that's where things are going. So, problems with POSIX and the outside world. The big data center. As another model we work with data, memory, SSD. So, we're in hard disk. Now we're moving. So we used to have classic rotating iron hard disks. Now we store our data in SSD, certainly on laptops and our phones, but also some of the data centers too, the servers, they're going to SSD memory. Again, we keep pretending that it's just another file. It's another file system. But it doesn't have to be that way, because actually we can memory mount an entire SSD disk and manipulate it if you feel like it. You can already do it. For a long time, you can do memory map IO in C and just say, use the OS swap system to page stuff in and out, and then maybe sync it. So we've had that API for a while, but it's not ideal, because once you start saying you're still treating it as a file, but actually, and this is where I'm at my depth here code-wise, is when you've got non-volatile memory, you can actually make a large chunk of your memory appear like it is non-volatile and basically persistent. You can have persistent memory structures that last outside a single application. This gets complicated fast, all right? This is still people are trying to come up with the algorithms and the papers on it. Andy's nodding over there like he's done it. Okay, there's some interesting work on it. But essentially, for example, how do you do a transacted write of a single record? Normally, code, you say, well, I write this field, I write that. Maybe if I'm doing something synchronized and get away with it. But actually, you've got to think about actually making that whole write atomic so that if your application crashes between the two, your persistent data set is not corrupt anymore. It's notable, Intel did actually provide some instructions for transacted memory, a couple of CPU releases back to try and support this, and they found bugs in them, because it's actually quite hard to get this stuff right. And the point is, you say, well, it's hard to do, but remember, a modern Intel CPU, you've got multiple cores and a big server, multiple sockets, and it's trying to do that distributed coordinated problem within a single CPU. So there's got great potential here. It's actually, instead of got more potential, it's easier to play with at the level of C and C++ because you can do pointer abuse. It's probably most dangerous for that very same reason too, I think. Someone's going to have to take this problem on. I would rather it's not me. But it changes how we have to think, what are we going to do about this? Well, because everybody here generally has written the program, has loaded things into memory, has done it in the knowledge that if ever they feel like it, when you kill the program, all your state is gone. And it's why it's, so it's really bad. But also it's like rebooting, restarting is the standard model of recovering from any problem in your system. So I'll just kill it and start again. But what happens if you've got persistent data? It's not going to go away. Or if you kill it and start again, you upgrade the application, and you're great, but your application assumes your data structure is version 1.3, but actually the persistent memory data structure is 0.2 release of your software. What are you going to do? So we have problems. I have no idea where to begin here, but it's very interesting. The morning paper by Adrian Kohler, he has some good papers on this stuff, actually. It's interesting. But the key finding is that you cannot take a data structure that you use in your application today and magically have it work in non-volatile memory. You have to start again from scratch. So, one more API, the dark API. I have nothing really against relational algebra. I do hate SQL. Hands up who knows SQL. Hands up who likes SQL. Hands up who understands about transaction isolation and levels of acidity in the database they use. Yeah. That was how one of the Bitcoin exchanges went bankrupt, because they didn't understand their isolation. For all its failings, SQL has been around for a long time. And it works. And it's funny, that a whole bit of the NoSQL movement, things like Hadoop and Spark and that, said, hey, you don't need to know SQL. But it just won't go away. And it won't go away for a couple of reasons. One, there are people out there that understand SQL that don't want to learn anything else because the other things are kind of a waste of their time. Two, query optimizers are actually really powerful things. Okay, you write your code in some kind of procedural language and think, okay, I'm going to do this, I'm going to filter by this, then I do this bit of the query and I chain things together. You're encoding in your head a set of assumptions about the structure of the data and the most efficient way to perform those transformations to give you your answer. Or you're not doing it very efficiently at all, one of those two things. But even if you're being clever, it might turn out that a year from later, those assumptions aren't valid anymore. The amount of data you've had changes, the location, all that kind of stuff. And the latest generation of those basically big data query optimizers, like Apache Carsite, they're actually better at coming up with query plans than us, the people. So SQL shall never die, I'm afraid, even if you hate it, just like me. You're just going to have to accept it exists. It doesn't mean that you should be using OR mapping or other things that are fundamentally wrong alongside SQL, but I'm afraid we are going to have to learn SQL. It's true. It's not like I'm lying. Anyway, example of how SQL will never die is Amazon now have added SQL queries into their object store. You can now query, if you store CSV files or Avro or JSON or Parquet files in Amazon S3, either raw or gzip, you can actually issue SQL queries against them. First, CSV is weird. A CSV is actually amusing in that it's kind of the dark matter of big data. And people go, well, what data structures do you have? It's like, oh, well, we use ORC. Oh, we're using Parquet. And it's like, I'm using CSV is actually probably one of the most popular file formats out there, which is, it's bad. And where it's actually really bad for, it's really bad at representing date and time. Okay, that's one of the things, it's just a nightmare of trying to pass strings of when things happen. This example here is actually some of the Boris Bike data set from London. And if you do a query again, what is the most popular time things get dropped off? It's January the 1st, 1970 as a string. And it's like, and it's a mess there, but it's things like escaping strings and all that kind of stuff. So it is a pain, but it is out there. And I think Amazon have actually decided to embrace it by saying, hey, it's really easy to do SQL queries against CSV. I am not convinced encouraging people to use CSV is good for humanity. But in its favor, it is easy to debug using the standard tool of head and tail. Okay, it's a tool. So I'm about to give a demo here then of me doing real live SQL queries against data sets. So here I'm basically going up against the US. I have a Landsat image, echo $, Landsat, GZ. I have a, okay, so I'm doing a query against a Landsat database that Amazon have somewhere in the East Coast. And it's got, let's do a quick header. I'm hopeless at typing SQL, okay? So we're going to basically do quick list here, edit this. This is probably going to fail. Select this, limit that. I want, no, I'm not going to. Right, so I've got a Landsat image here. I'm basically going to say it's compressed, time it. I'm going to do a query here of, this one here, right. I'm basically using a normal Hadoop stack. I'm saying, download this, uncompress it as you go. I'm going to grep for the string 0,0 in it. Show me it's going long. So this is me doing a query. And I'm basically finding things with cloud cover, just doing a string pattern match. And took a bit of time to start up. That's me just kicking off the GET request. And it's churning away. We're doing the filtering there. And it's taking time. Because all that data, it's a 400 megabyte file, is coming down from the East Coast US, where my application is now actually analyzing it. And it'll go on for a while. Now, this is the worst case scenario. We're coming over a transatlantic link. We're using Wi-Fi. But actually, if you're running an Amazon's EC2 infrastructure, the bandwidth of S3 can be pretty patchy as well, especially in the budget. You're nodding there, aren't you? Is the lower cost, affordable EC2 VMs have less bandwidth. than the higher ones do. So S3 is pretty slow, and it's some aspect of their architecture. So let's just stop that running away. Come on, Control-C. There we go. We gave up after a minute. Now I'm going to do exactly the same query in the S3 select. So select star from S3 object of S where s.cloudCover equals 0, because it's using the top row of my CSV file to provide the schema, I say in quotes. So let's do it. Boom. Oh, wrong header option. Okay, what did I do there? See how long it takes this time. So now I'm trying to do select. So that was the whole select, 11.556 seconds elapsed time to go through a 400 megabyte file, strip out all the things where the cloud cover was 0. And that was because all the heavy lifting was happening in Amazon storage. I only downloaded the answers. All right? That's kind of slick, isn't it? It's interesting. The thing is, it's still kind of the way you can really have fun is when you start projecting stuff as well, because it downloaded every single row. But you can also say, I only want one field at the top. So now, we're not only doing the filtering, we're actually getting back some, well, we've got nothing back, actually. Things should come back faster. Obviously, I've got the name of the field or something like that. But the point is that by putting SQL into the file system, Amazon have done something that is both terrible and wonderful. Wonderful in that you can do SQL queries against your data before you even load it. Terrible because you're using SQL and you're doing SQL against CSV files. So there we go, real live demo. So there's the key point. It's all built up in my head, a model of the world that is built around floppy disks and file systems with trees of directories, and directories have files, but you can't put a file under a file or a directory. And certain operations are fast, like listing a directory, like tree walking. Renaming is not only fast, but it's atomic, so we can use it as the foundation for actually committing all our work. And I'm afraid that world is it's over. You can pretend that it's still there. A lot of people doing the tooling, we try and put a lot of effort to make it pretend it's still there so that you can take all your skills and assumptions and move them to the new world. But when you look closely, you have to recognize that those assumptions, they're not valid anymore. Trying to maintain the metaphor is potentially dangerous for things like committing work. And abandoning the metaphor can actually make things a lot faster. We're going to need some new APIs for this. But we can actually improve how things go once we say, maybe it's time to move on. That said, someone's accused me of basically, this is the no POSIX manifesto, the way the no SQL will be. It might come 5 years from now, people go, hey, POSIX is so much better than anything we've done before. We'll see. But anyway, so it's there, it's the future, and if you can't handle it, use SQL and let somebody else deal with it instead. Now, that is the end of the talk. Are there any questions? Hello, yes. There's a microphone somewhere.
There is. I've got one. You were talking about the difference that non-volatile memory makes. And I suppose in RAM world, you think of persistent data structures like there are in Scala, where you don't have overwrites. Mm-hmm. And I suppose the immediate thing is, well, try and postpone and minimize your updates. Is there a kind, for non-volatile memory, is there a kind of API which is like compare and swap? Is there something really simple that you can?
Good question. I haven't actually looked at that at all. Okay, I've read through some of the papers, and one of the things that people seem to do in existing code is we mix the bits of the data that's persistent with the transient bits as well. We blur them all in as we kind of load that stuff in. And then we often cross-reference other records using pointers. So in a world we have an NVM, you could say, well, I'm going to create a new bit of structure in the NVM and just update a single pointer. So you can build a whole tree and switch stuff over. So in that world, one single pointer write, which is effectively memory renaming, gives you some of that semantics. Okay, I don't know about anything else in detail at all. Okay, it is very low level, and I've not played with that at all. Okay, but yeah, some of those things where you're not doing in-place updates are probably safer in this world.
Can you explain why you're so against manipulating files that are in CSV format?
Can I explain why I'm against manipulating files in CSV format? There's actually a conference called CSV World. You think I'm taking the piss, don't you? All right, so one of the things is that actually, if you do, some of the most important data on the planet for organizations is actually in spreadsheets. Okay, it's incredibly buggy data, but it's there. It's just, it is not a great format, and it's not good for hierarchical data structures at all. You basically got one single flat row. I believe Spark has a problem once you have more than 1024 elements in a single CSV row. But it's just, you want it, if you have a single record, you want more complicated data structure inside it. CSV just doesn't cut it. Okay, if you look at any other object stores, you can do it. JSON, single record JSON is pretty inefficient. It's pretty verbose. And you get to weird fun there where you have different records and you don't, it's all schemaless. I'm a great fan of Avro, actually, because it saves a schema at the top of the file, and you can have more complicated record structures. And you're not really, it's fairly simplistic to actually write Avro. You can just stream it along as you go along. That said, I spent the Christmas last year writing a version of Ping that outputs CSV files, because the great thing about CSV files is anything can print them. Okay, you just use printf, and you're pretty much done. So it's actually, it's quite good as a kind of the ingress format. CSV is actually kind of cute. But for actual analytics, it's just wrong. So what we do is when you look at some of the formats like OSC and Parquet, the striped columnar data, we have more complicated structures which you save inside, and you pull out different sets of columns. So when we analyze it, we don't analyze immediately, say you have like 5 gigabytes worth of data. We don't scan it all. We just read a footer. We know where the columns are split up. And say, okay, we only want these columns that we're projecting. Here are the columns we're filtering on. So we go in there, we read those columns, we scan them to decide, okay, we've scanned this column, we know that these matching rows are the ones we want, so then we go to the bit of the file where those the columns of the rows that we're projecting are, and then we just output them. So we can do a lot less reading. And because we know exactly where in the files these stripes are, once you've read the footer to know the length of the file, then that's why we can do that asynchronous block I/O stuff, is we know roughly what we're going to be reading on our first scans. So we can do it very efficiently. CSV doesn't let you do that. Those SQL queries that we kicked off through Amazon, it's still having to go through row by row filtering.
It doesn't, under the hood, have any metadata that tells it what the underlying structure actually is.
Nope. No, they're adding Parquet support, actually. They've announced that recently, so they might be able to do that. We're kind of a bit worried about that, because we have to support things like that, is actually if there's a bug, who is going to fix it? If it's like CSV is tractable, and you can fall back to saying, I'm not going to use CSV. So it'll be interesting qualifying that. But the fact that Amazon is supporting that, I think they're admitting that CSV works as a format. It's kind of, yeah. The thing is also, is it CSV, is it tab separated, is it a single quote, is it a double quote, how are you going to represent time? It's not really a format, it's more just a kind of text when you think about it, isn't it?
Jason's still cracking that one for you, though, isn't
Yeah.
Sorry, I was saying another lovely thing about the columnar formats is Another lovely thing about the columnar formats, like Parquet, is the compression they apply. And you get a lot better compression down columns than you do across rows. So with current transaction data, I've had compression up to a factor of 50, which really improves time because it's easier or cheaper to decompress stuff in CPU than it is to read blocks on disk.
Anybody else got a question?
Okay.
In which case, thank you very much, Steve. We finished about 20 minutes early, I think. So,
Ooh.
I think. Yep. Feel free to go and see the exhibitors, get yourself a coffee or whatever. The closing session will start.
Thank you. Thank you all for coming.